Simpson's rule is a very accurate method of estimating the area under the curve, but it can be very tedious, particularly for large values of n. The calculation is very similar to the calculation you would do for a Riemann sum, only Simpson's rule uses small parabolas rather than rectangles. Simpson's rule follows a template equation which can easily be automated on your calculator. The template has a couple of notable features. One is that the function values at each x interval are multiplied by a constant coefficient. The first coefficient is 1, the last coefficient is 1, and the intervening coefficients alternate between 4 and 2, starting on 4 and ending on 4. The delta x is divided by 3 and is calculated in the normal way, b minus a over n, which is the upper bound minus the lower bound divided by n. The n must be an even number. We'll do a manual calculation first, and then we'll show how this can largely be automated on the calculator, which of course makes it much less tedious. So here's the manual calculation. We want to estimate the area under the curve of f of x equals 1 over x from the lower bound of 1 to the upper bound of 2 using Simpson's rule, and our n is equal to 4. We calculate the delta x, which is b minus a over n, so that's 2 minus 1 divided by 4, which is 1/4. So our delta x is 1/4. That gives us our x values, which are 1, the lower bound, and then 5/4, 6/4, 7/4, and 2, which is our upper bound. Our equation then will become, for a Simpson's rule estimate, 1/4 divided by 3, which is our delta x divided by 3, times 1 times 1 over 1, that's our function value at the x value of 1, plus 4 times 1 over 5/4, that's the function value at our second x value, etc. If we do the calculation, we end up with a Simpson's rule estimate using an n of 4 of 0.6932539. That's not a bad estimate, even with such a low n. If we perform that integration on our calculator, the answer is 0.69314711806. So it was very close. That manual calculation wasn't so bad, but what if we need more accuracy? What if we have to use an n of 10 or 20 or 50? That is extremely tedious and time-consuming to perform. That's where the calculator comes to the rescue. Using the calculator, we can create a list. We're going to call it x, that contains all of the x values. We'll create another list, call it y, that has all of the function coefficients. The Casio calculator, and in fact many calculators, have the ability to multiply one list times another, and they will multiply the first element of one list times the first element of the second. They will multiply the second element of the first list times the second element of the second, etc. I can give you a short example right here. If we use the calculator to create two lists, I'll say 1, 2, 3, and I'm going to multiply that by another list. We'll call that 3, 4, 5. It performs the calculation element by element, and we end up with 3, 8, and 15. And then if we needed to or wanted to, we could sum up those values by going to the action list calculation sum command, copy this, drag it over there, and do the sum, and our sum is 26. These are the types of calculations we're going to do Simpson's rule. Our equation on the calculator for Simpson's rule is going to be the sum of delta x divided by 3 times y, which includes our coefficients, times f of x, our function values. Since our f of x in this example is 1 over x, our equation is going to be Simpson's rule estimate is equal to the sum of delta x divided by 3 times y times 1 over x. So here are the steps that you would use to set this up. First, we're going to create a list of the x values. On the Casio Classpad, which I'm using, click on Interactive, List, Create, and Sequence. You're going to be presented with a form. Enter x for the expression. Leave the variable x at its default. For start, enter 1. This is your a, or your lower bound. For end, enter 2. This is your upper bound. And our increment is our delta x. So in this case, it's going to be 1/10, since the n that we chose is 10. So 1 divided by 10. We click OK, and it created our sequence for us. I've got it in decimal mode, so it created the list of 1, 1.1, 1.2, etc. Now we want to go ahead and store that in the x variable. So I'm going to go back up to it and tell it to store this into x and hit enter. And it has now stored that value in x. Now we need to create our sequence of coefficients. We're going to do this in 2 steps. First, we're going to create an alternating sequence of 4 and 2, starting at 4 and ending with 4. So, we create another sequence. Click on Interactive, List, Create, Sequence. Now for the expression, enter 3 plus -1 raised to the x power. We leave the variable x at its default. Our start value is 2. Our ending value is the n that we chose, which in this case is 10. And we leave the increment at 1. We click OK. And that produced our alternating sequence of 4, 2, 4, 2, 4, 2, 4, 2, 4. Now we need to prepend a 1. So we're going to select that. Prepend a 1, comma, and at the end we're going to append a 1. And we're going to save that into the variable y. Alright. Now that we've done that, we're ready to do the calculation. First, we want to sum these values, so we're going to go to Action, List, Calculate Sum. We're going to multiply by the delta x divided by 3, which is 1/10 divided by 3, which is 1 over 30. We're going to multiply that times y, which are our coefficients, times the function values, which is 1 over x. Close up our parentheses and hit execute. And we end up with 0.6931502,307. That's a very good estimate, and in fact closer to our known value than the estimate we had at n equals 4. If that's at all unclear, we can do this on another problem just to try to hammer it in. We want to use Simpson's rule with an n equal 4 to approximate the area under the curve of the function f of x equals 9e raised to the -1/2 x, and we want to do that or estimate that value from a lower bound of 0 to an upper bound of 4. Our delta x in this case is 1. That's 4 minus 0 over 4, which is 1. And we set this up in the same way we did before. We create the x list. So we're going to go to Interactive, list, create, sequence. We leave x as our expression. We start at 0, we end at 4, and our increment is 1. Hit execute. I want to store that into x. Now I need to create my alternating 4s and 2s. So I go to interactive, list, create, sequence, enter my expression again, 3 plus -1 raised to the x. I start at 2. I input my n, which is 4. I leave my increment at 1. Select OK. And those are our alternating 4s and 2s. I need to prepend the 1. I need to append the 1 and store that into y. Now I'm ready to do the calculation. So this is sum of delta x divided by 3, which is 1/3 in this case, times y, times our function values, 9e raised to the negative 1/2 x. Close up my parentheses. And there's my Simpson's rule estimate of 15.56921,234, which is very close to the known value. If we put it into the calculator, we get 15.5639649. If this were a function in which we were unable to do the integration, we could, with very little trouble, use Simpson's rule to estimate the value and recalculate with a much greater precision using an n of 10, 20, 50, or whatever.